Hello, my name is Betsy Hoflinger, and this is the final presentation for ME372 design of mechanisms. The final project required a design and analysis of a 4-bar mechanism, and I chose to do my analysis on a windshield wiper. All right, so first of all, just a little bit of background on the windshield wiper. Mary Sanderson actually invented and patented the first ever in-vehicle windshield wiper in 1903. There is a picture up on the top left in figure 2 of that device. Let me get my laser pointer here. There we go. Here is the first in-vehicle windshield wiper. And then in the 1960s, Robert Kearns invented the basis of what we use today as a windshield wiper. And it's actually kind of funny how that happened. He actually had some sort of accident with his eyes, and it affected his driving. And so that led him to want to create a wiper that had more, options and worked on a time system as opposed to having to do it manually. So the goal for this project is to identify the design criteria as well as the constraints, and then synthesize or design a wiper with real life dimensions, and then analyze that. And I will be doing that with a kinematic analytical analysis. So with the design requirements, this model, so these are just a couple of examples. In this bottom figure is just a generic windshield wiper that we see today. And there is another similar one here that I'm pointing at now. You see the difference is that point A on the bottom figure is kind of wrapped in and in the middle of the two rockers, where on the top one, the crank is positioned in the middle of them. So there's various designs to this, and while researching, I did see several different designs. So the one wiper is attached to the crank. So if you just, like, for example, if you look at this one, crank is point A, it's attached directly to the crank coupler and then this left rocker. And then the other windshield wiper is attached to the right rocker. So one is a Grashof and one is not. Something cool about windshield wiper is that these should be parallel at all times. So the one motor that runs the crank operates both the wipers via a parallelogram linkage. So as one moves, the other moves, just how you see in your car. So the inline design is what I just described. It's the motion of the crank that provides symmetrical motion. The forward and backward stroke should be identical. And then last here on this page, we have how I found the degrees of freedom, and using the equations learned in class, I found that to be 1 for this type of wiper. So here's the design tasks. We're supposed to synthesize a 4-bar mechanism using real life dimensions. I've assumed the lengths based on just some research on windshield wipers and what some generic lengths of the different lengths of those are. So for this analysis, up here in the top right, you see the full windshield wiper mechanism that I used. And similar to the last page, the crank can either be in the middle or outside. I chose to put it out to the left. And then this way, we have this 4-bar mechanism here that operates the entire system. So we'll be doing the analysis on this 4-bar mechanism here. The vector polygon or analysis is here. So you have your crank, which starts here, and then your theta2, which is the angular displacement of the crank, which then affects the other 3 links. So you have your imaginary axis, your real axis, or your y and x axis. And then I use those centimeter dimensions that you see in the top picture to create this vector polygon analysis. So then I identified the real and imaginary components, as you see here. These are my equations. And from there, you can generate the loop closure equation. So here is my closure equation. And here we have theta3 and theta4, which are unknown and also dependent variables. So from there, we can find our H values, and then furthermore, your A, B, C, D, and E values. And this is just a screenshot from one of our lectures where I generated some of those calculations from those equations. So further on the design text, and this is the complete analytical kinematic analysis here that you'll see on the screen. So first, I solved the loop closure equation for positions. So for theta3 and theta4, I found that theta3 to be 32.2 degrees and theta4 to be 102.2 degrees. And then correlating to those equations up on the top right, you'll see the position versus angular displacement of theta2, or as a function of theta2. So you see the legend here, we have both theta3 and theta4 as a function of theta2 mapped out here. And then to find your angular velocities, you take the time derivative of the position equations to solve for your theta3 dot and theta4 dot. So those equations are here. I found theta3 dot, or also known as omega, to be 7.9 radians per second, and then omega 4 to be negative 21.1 radians per second. These are both graphed off to the right as a function of theta2 again. And then last but not least, we have the get the angular accelerations as function of your theta2 input link. You have to take, again, the time derivative of your velocity equations to get your theta double dot 3 and theta double dot 4, also known as alpha over here, so don't get confused. This theta dot is the same as omega, theta double dot is the same as alpha. So I found alpha 3 to be 1218.6 radians per second squared, and alpha 4 to be 142.8 radians per second squared. Again, off to the right, you can see the graph that's showing your angular accelerations as a function of theta2. And after that, that has completed the vector analytical analysis for this 4-bar link mechanism. And next is just my reference page. And hopefully you enjoyed, and thank you.